In this last section on community finding, I'd like to discuss how one actually goes about discovering communities in networks. We talked about how simply looking for cliques or K-cores, etc., how that can be a little bit arbitrary. What if we had a criterion that said, once you've partitioned the nodes into these groups, so the key word is for now is that we're partitioning, we're chopping the network up, that we can say that this is the optimal way to chop the network up with respect to some criterion. And these would be the natural communities that exist in the network. The trick is just to find them. One approach is hierarchical clustering, where you compute some similarity between the nodes and you, to start with, each node is in its own component, in its own community. And then you find the two nodes, for example, that are most alike. And this similarity could be things like how many neighbors do they have in common, or if you have a weighted network, how often do they communicate with one another. Regardless, you have some notion of these two nodes are close, they're similar, and you start agglomerating in this way. And there are, of course, some decisions you have to make. Do you pick the node that has the minimum distance to a node in the existing cluster, or do you look for the average similarity being the highest, etc., right? So there are different options in hierarchical clustering, but one nice thing is that as you're aggregating up and up, you can, and finally you have the whole network is in the same component or same community, you can then decide at what level you would like to cut. And so depending on how low you go, you have very refined community structure or very coarse community structure. Now, there is a very efficient and successful implementation of this in Payek and some other software. To my knowledge, it's not implemented in Gephi, and I've looked a little bit at iGraph and NetworkX, and of course, these are things that you can sort of implement yourself if you're a programmer. So let's leave hierarchical clustering for now. It is definitely an okay way to approach finding communities and networks, but it doesn't necessarily fulfill this criterion of we have some single metric that we're trying to optimize, right? Hierarchical clustering is just more organic. We're going to keep lumping together nodes and groups of nodes until it's all lumped together, and we're just going to somehow decide where we want to stop, but we don't really have that stopping criterion yet. If we go back to the Zachary Karate Club, I just wanted to illustrate what this might look like in Payek. So if you remember, this is the club that broke up, and we just wanted to see what would a community finding algorithm have predicted would happen, who will go where. So I had somehow managed to accidentally delete the last part of this lecture, so this is a little bit of a redo, so apologies for the disconnected flow. Where I was at was looking at hierarchical clustering in Payek for Zachary's Karate Club. That is, can we predict that these folks are going to go one way and the rest of these folks are going to go another? Before we do that, we're going to look at the adjacency matrix in a pretty neat way. What I've done is I've used Payek to color each entry in the matrix where there's an edge as black. And you can see the way the data was originally entered already betrays some structure. However, it's not very clear how many different communities there are. If we were to randomly permute the rows, we would get, so this is the same network, it's just that which vertex has the label 13 and is in the 13th row is different in this matrix than it was in the previous one. And here we can see very little structure, right? This is a random permutation. after we perform our hierarchical clustering, we can repermute the matrix such that those nodes that are in the same cluster are placed close together. And now we can see clearly that there are two distinct communities, each with one or two very central individuals. One other form of output is the dendrogram, which tells us as you join nodes and groups of nodes together that are similar in this hierarchical clustering process, you can see which nodes are in the same group. And eventually you end up with just two groups, which then you can compare. Are these individuals the ones who split off? This next way of clustering the network was proposed by Mark Newman and Michel Girbon, and it's very computationally inefficient, but it's also quite intuitive. So I'll cover it just as a way of building our intuition and also using this approach where we're allowing the clustering algorithm to work on its own rather than saying, oh, there must be a clique, and then just having different stopping criteria, just like we did with the hierarchical clustering in Payek, where we had vertex similarity deciding who's going to be joined. In this case, we're going to be starting with a complete network and we're going to be taking edges away. So we're going to be deconstructing it and getting finer and finer grained communities. Now, the basic idea behind this is that there's some edges that have high betweenness. Edge betweenness is, really the same definition as node betweenness. It just counts the number of different shortest paths that pass through an edge. And if an edge has high betweenness, that means it's between different sets of nodes. So removing that edge might then reveal what these different sets of nodes are, because it might actually, if you keep doing this, disconnect those communities completely. So say we have a network such as this one with two fairly clear communities, we might expect that these edges in between here are the ones with high betweenness. And what we're going to do is we're going to iteratively find the one with highest betweenness, remove it. Now we recalculate, and this computation is expensive. That's why this algorithm is slow and doesn't scale to really large networks. But we'd find the next one, remove it. We'd find the next one, remove that one. And by doing this iteratively, we get successively finer and finer communities. For example, first, in this case, separating out into two disjoint communities, and then four smaller ones plus two kind of nodes which become isolated. And if we evaluate this algorithm, we find that for the Zachary Karate Club, at least, there's only one node which was miscategorized. And, who is to say that this wasn't a more true affiliation for that node, but for whatever other factors, it went the other way when the split happened. The problem with hierarchical clustering and with this betweenness community finding algorithm is that there isn't a clear stopping criterion, right? It's great that you can stop at different resolutions, but how do you know which one is optimal, which one might be the true community structure of the network? So Girbon and Newman went back and they formulated this measure of modularity, which is going to tell us, at some point, we're going to maximize this quantity. And when we do that, we're going to have the most edges within the community, much more so than you would expect at random with this particular community partition. So what we do is for each node, we assign a community C. So vertex V is in community C sub V, and vertex W is in community C sub W. And now this is just a delta function. So this is going to be 1 if W and V are in the same community, and it's going to be 0 if they're not. So this function is going to sum just over the nodes which are assigned into the same community. And really this is algorithm agnostic, so you could be doing the betweenness clustering, you could be doing hierarchical clustering. It doesn't really matter. You can always calculate the modularity. So the question is, if V and W are in the same community, how many edges do we observe between such nodes in the same community? So we're just going to sum over the adjacency matrix, and then we're going to subtract how many edges we would expect at random, because C and W have degrees, so V and W have degrees, so case of V is the degree of V, and case of W is the degree of W. And so just by chance, these two may have linked to each other. The higher their degree, if they're two really large hubs, there's relatively higher likelihood that they'll be linking together than if they each have degree 1. And so that's just what we're doing. We're looking at the actual number of links within the community versus how many links you would expect based on the degree of those nodes that have been assigned to the same community. And we're doing this for all pairs of nodes. And for a random network, there would be no difference between or actually also for a random community assignment, there'd be no difference between what you observe and what you expect on average, and so your modularity would be 0. So an algorithm that can then use modularity is, again, a hierarchical approach where you start with all vertices as isolates. But now, rather than joining together vertices or groups of vertices that are similar according to some measure, we're going to join the ones such that the modularity increases maximally. And so we can keep doing this until the modularity no longer increases, or we can actually go beyond that point, allow modularity to decrease, but we still have a way of kind of minimizing that decrease and also getting larger communities. So this is very scalable up to very large graphs, and there is code available if you want to just download it standalone, but very nicely it's also implemented in Gephi. A reminder of why you may want to do this, here is some work, again, by Mark Newman, where he looked at, I think these are the scientific collaborations at the Santa Fe Institute. And rather than looking at, oh, there's this big network and everyone's working on something, you can find groups of researchers who are working on the same thing. And then you can even do something like visualize the metanodes, where one metanode represents everyone in the same community, and now you can start to see the relationships between these different groups. In this case, it would be how different groups of researchers cross-collaborate. One thing that I haven't mentioned that explicitly so far is that for the algorithms I've mentioned, we're really partitioning the network. We can't have one node be a member of two different communities. However, in a real-world network, this is hardly the case, right? When you looked at your Facebook network, you may have seen distinct communities. However, you have to be aware that that was a slice. That was a slice of that individual's network that pertains to you, and they probably know you through a single context, or at most two contexts. So that's someone you know from school, that's someone you know from work. But each of those individuals has lots of other contexts, so their other school or their other work that's not related to you, and this gives a very dense interlinked structure that's very hard to partition in the way that a lot of these algorithms would like to do it. And Yuri Leskovitz and his collaborators at Stanford have found that for many large social networks, the huge ones, precisely the ones that you would really like to be able to partition so you can study little parts of it, it's almost impossible to do so. So networks such as Flickr, Orkut, the Microsoft Instant Messaging graph, none of these are easily partitionable, And they found that at most, communities of 100 nodes can be separated, and everything else is too overlapped to do it. So what comes to the rescue then are community finding algorithms which allow for overlap, which allow nodes to be members of more than one community. One such piece of software that allows you to find overlapping communities is Clique Finder, which you can download for free. The basic idea there is that you're going to roll cliques around. It's a form of clique percolation. You're going to see how many steps you can take when the rules are as follows. You're going to choose a certain size clique, say a 4 clique, that is 4 nodes who each have links to everyone else within the clique. And then at each step you can omit one of the nodes and add another one, as long as that step allows you to form another clique. And you keep doing that until you can't move any further. So for example, here we have these 4 nodes in a clique, and then we can leave this one out and oops, sorry, and get this clique here. And then finally we can leave this guy out and get this clique here. And in this way we can get overlapping communities, which is very relevant for social networks. It's very relevant for biological networks, and it's just plain more flexible to find overlapping communities than to partition the network in a choppy way. So just to wrap up, what we've tackled this week is that large networks can be giant hairballs, and if we can identify distinct regions within the network, that can give us important insights. Are these functional groups within the cell? Are these areas of research within science? Are these individuals who are collaborating within an organization? Now, how we approach that discovery of interesting structure is partitioned into two different themes. The first one is that you're going to look for specific structures. For example, you're going to look for cliques or K-cores. But if the network actually doesn't exhibit this structure and it exhibits some other structure, this approach can be too rigid. So what we talked about now most recently, and what's been popular definitely in the past 10 years or so, is looking for more organic approaches which let the community structure show itself to you. And you can use methods or metrics such as modularity to see whether, well, first of all, to try to find that organic partition, but also to evaluate any sort of community finding algorithm insofar as did it place nodes in the same community in a way that had much greater density of edges within the community than from those nodes to other places, other parts of the network. Now, for the assignment, you'll be looking at ingredient networks. So here is the network of ingredient complements. These are things that go together often or that co-occur often. And here is oh shoot, what's the sandwich called? The sauerkraut and corned beef and Swiss cheese. How can I? Oh, it's a Reuben sandwich. That's right. And I wanted to show you one other web application that isn't going to be part of your assignment, in part because I don't want to overload their server, but that I think is very neat and uses an information theoretic approach that I will provide the article for, and you can check it out yourself. I mean, I think that that article is just testimony to the many different creative approaches, really fun approaches that people have taken to discovering communities in networks. So let me try and switch over to that site. Okay, so I'm going to load my network of substitutes, and I'm going to do the directed network. And I'm going to calculate clusters. Cool. So each one of these clusters now is a set of ingredients. So if I double click on this one, I can find that it's clustered chicken and turkey and beef and sausage and chicken breast together as ingredients that are frequently substituted for one another. We can also, for example, look at olive oil and find olive oil substituted by butter, substituted by applesauce. I didn't know this until I was doing the research, but I guess applesauce is often a low-fat alternative that gets substituted in. Now, let me see if I can find, there's a neat kind of subgraph. Explore subnetwork. Cool. So here we have the subnetwork of the most common substitutions. So it looks like maybe applesauce is common both for butter and oil, but not, as I said just a second ago, for olive oil, right? So maybe if you're putting in the extra effort to use olive oil instead of any old oil, you're also less likely to then go for the applesauce, which, you know, may be lower calorie, but maybe doesn't taste as good as olive oil. So with that, I'll close out week 4. I hope you have fun with the assignment, and next week we'll be talking about small world networks. So going back a little bit to modeling and understanding the structure of these networks. Where does the community structure come from, and what implications does it have for things such as diffusion of information or the ability of individuals to find information within the network? So see you next week.